Another method of solving higher order non-homogeneous equations is actually using variation of parameters. In order for us to use that said method, let's try to introduce here the Wronskian of a function. Because for variation of parameters, we will be using the concept of the Wronskian. Now, for a Wronskian of a certain function, it's actually related to the determinant of a certain matrix. The matrix involves the functions and their specific derivatives. Suppose we have these functions here. Let's say our first function is f sub 1 of x. And then later on, our second function is f sub 2 of x. And let's say if we have f sub 3 of x, and assuming that we have f of n of x, we have n number of functions. Okay? The Wronskian of this function is the determinant of an equivalent matrix considering this and n minus 1 derivatives of each of the function. And the derivatives are actually written in a specific column, the same column with our function. So say for example, we have here n number of functions. So let's try to solve for n minus 1 derivative of each, again on the same column. We have here f sub 1, its first order derivative. We also have here the first order derivative of f sub 2x. We also have here the first order derivative of the third function. And we have here the first order derivative of our nth function. We have here the second order derivative of our first function. We have here the second order derivative of our second function, the second order derivative of our third function, and the second order derivative of our nth function. Until you will reach here the n minus 1 derivative of our first function. We have the n minus 1 derivative of our second function. We have here the nth minus 1 derivative of our third function. And we have here the nth minus 1 order derivative of our nth function. They are written in the specific column. Now, notice that this if we're going to come up a matrix with this, okay, this matrix is actually a square matrix. Why? Because the number of columns here is actually, there are n columns, okay? There are n columns and n rows as well. Even if our last derivative is n minus 1, we started with the original function. So n minus 1 derivative plus this original function. So we still have n number of rows. Hence, it's again a square matrix. Now, we know that we can only get the determinant of a certain matrix if the matrix is actually a square matrix. So the determinant of this matrix, okay, let's say it's actually denoted, let's say if this is our, let's call this as matrix A. The determinant of matrix A is actually equivalent to the Wronskian of the functions f sub 1, f sub 2, f sub 3 until your f sub n. Okay, we know that the determinant is actually the sum of the products of the diagonals or the the components of the matrix multiplied for this order here. Okay, and then we have the next one until the first one here. Of course, we know that that is the process until somewhere here and everything, and then minus the result of these functions here, the next function with the first one, this function, and the next one here, and so on and so forth. So the determinant of that is equivalent to the Wronskian of the functions identified here. I'm not going to give specific examples here. We will have specific examples as different videos later on. But just for an illustration, say for example, if you have three functions, f sub 1 of x, f sub 2 of x, and f sub 3 of x, so that we will be able to understand and appreciate that it's actually a square matrix. So we have n being 3. So we'll have n minus 1 derivative. That means 3 minus 1. So we'll end up until the second order. So we have here the first order of x, the second order of, the second order of, yeah, that's right, first function, the first order of your second x, the second order derivative of your second function of x, the first order derivative of your third function of x, then the second order derivative of the third function of x. As you can see, we ended up here with n minus 1. Still, we came up with a square matrix. It's a 3 by 3 matrix. Hence, determinant is actually possible here, which again corresponds to the Wronskian of the given functions. Again, as mentioned, we will have specific videos on the determination of specific Wronskian of functions, specific functions, and later on solve some higher order non-homogeneous differential equation using variation parameters, which would involve the concept of Wronskian. Please stay tuned for those examples. Thank you very much for watching.